Good evening, ladies and gentlemen. It is a great pleasure today for me to introduce you tonight's speakers, Eric Drexler. Eric Drexler is often considered as the founding father of nanotechnology, and he gained worldwide fame for his popularization of this subject for a general audience. He is not only a scientist, but he is also a writer, as many of you might know. Apart from having written several books on this topic, he also co-founded the Foresight Institute for the awards for a Feynman Prize for the most important achievements in nanotechnology. Perhaps less well known is that on his early career, he was also heavily interested in space technology and space colonization. Eric obtained his master's degree in MIT, Massachusetts Institute of Technology, with a thesis in 1979, with a thesis entitled Design of a High Performance of Solar Cell System. Around the same time, Eric encountered a lecture that Richard Feynman gave in 1959, entitled There is Plenty of Room at the Bottom. And I guess that was highly inspiring for him, for his nanotechnology ideas he developed. This resulted in the publication in 1981 of a seminal paper in which he, for the first time, described the fundamental principles of engineering at molecular level. His first book, Engine of Creation, was published in 1986, and he introduced the concept of nanotechnology to a broad audience at that time. In 1991, Eric obtained his PhD on the subject of nanotechnology, and I believe it was the first of its kind at that time as a subject to have a PhD thesis on, also from MIT. His thesis was published also after 1 year as a book, and it was entitled Nanosystems, Molecular Machinery, Manufacturing, and Computation. And it received the award for the best computer science book in 1992 by the Association of American Publishers. Although nanotechnology, just as any type of technology, can have an aim for different purposes, Eric's focus is on how advanced nanotechnologies can be used to solve global problems. For example, he has worked with the World Wide Fund to explore ways in which nanotechnology can help to solve problems like, for instance, global warming. Eric is also a chief technical advisor of NanoRex, a company developing open source design software for structural DNA nanotechnologies. Currently, Eric is an academic visitor at Oxford University, where he also wrote his latest book, Radical Abundance: How a Revolution in Nanotechnology Will Change Your Civilization. So I would stop here to continue the long list of what Eric's achievements are and ideas, and I think without any further delay, I would like to invite Eric to share with us his ideas on how exactly nanotechnology has developed from the moment he introduced the concept and where actually it can lead us. Please, Eric, I would like to give you the...
Thank you. Thank you, and I'd like to thank the organizers of this event for an opportunity to speak to you this evening about a line of technological development that I think can have a profound effect on our future in the 21st century, making possible a different kind of world than what is widely assumed today. And my aim here isn't to say, this is the future, this is what will be, but rather to say, here is a line of reasoning based in physics, textbook science, engineering principles that indicates that there are certain possibilities for the future of manufacturing, for our ability to make things, that can be a revolution on the scale of the Industrial Revolution and change civilization at its material foundations. So the claim is that if one looks at the facts, actually evaluates the science and engineering, that one is led to certain conclusions which call for further investigation and I think a serious beginning of a reconsideration of our expectations and research priorities. So of course the book also has another title, now being available in Dutch, which is why I'm here today, invited by the publisher to give talks and many interviews. Exhausted. Many interviews in the last 2 days, but I'll try to make my way through this presentation anyway. Okay, so the key technology here is what I think is best termed high throughput atomically precise manufacturing. The concept of nanotechnology that created much of the initial excitement was one of high throughput atomically precise manufacturing, not by that term, but that capability. And I will be, of course, talking more about that technology, but I would like to emphasize that behind this story is a key knowledge question, which is how can we understand the prospects for genuine revolution in technology? It's natural to assume that, well, you know, something in the future, a great change, there must be, that it must be very hard to draw any firm conclusions. And it turns out that that's a matter of what questions you ask. The way to lead to some, the way to pursue inquiry that leads to solid conclusions is to ask the right questions. One question you can ask is, well, what will science discover in the future? You know, you can't predict that. If you knew what you would discover, you would already know it. So it's not even logically possible to predict the content of future scientific discoveries. One might aim to predict specific technological developments, but often there are unexpected inventions. And in particular, if you're asking what technologies might win in the marketplace, well, if you could do that well, you could make a lot of money in the stock market. Predictions are very difficult because they would involve not only understanding the technology that you're considering, but all of the alternatives. And often there's some alternative that someone invents that's better. So one has to take account of that in thinking about the potential of technology. But there's a difference question, which is one that involves exploring what can be thought of as the timeless potential of technology. And what I mean by that is that advanced technologies, in a sense, don't have anything to do with the future. They're not fundamentally about the future. They're fundamentally about natural law. The laws of physics determine the behavior of matter and energy in the world, the initial conditions to outcomes, not just the motion of planets, but the behavior of mechanisms, of useful technological artifacts. And the potential of technology is an abstract aspect of the structure of the world, of the structure of natural law. The potential is the same today as it will be in 1,000 years, and the same as it was long ago in galaxies far away. It's something that was born with our universe. It's a landscape of possibility that we can explore if we ask the right questions and use the right methodologies and have enough scientific knowledge. And we can learn something about that potential. And the key is to look for reliable answers to well-chosen questions, and those are the questions where engineering methodologies apply, and there are large margins of safety so that the unknowns are boxed and controlled. And the result is conclusions which can be investigated. They're based on textbook physics and engineering. There are numbers, concrete descriptions. One can check the numbers. One can ask, is something left out? And I think draw clear conclusions. And what I do in the book is to frame the questions, present what I think are some of the answers to very basic questions, and then ask what are the implications of some of the capabilities that this line of development points to. So when I speak of a line of development, I think it's useful to look back in history and how did we get where we are today. Once upon a time, our ancestors didn't have a lot to work with. They had stone and bone and wood and fiber, and used those things to make tools for a very long time. It was almost a million years that our ancestors were using hand axes. But eventually, we learned to use tools to dig and build fires and refine metals. And eventually, we had a technology of blacksmithing, which was working with a rather robust materials of iron and steel. And over time, blacksmiths used their tools to build better tools, to develop better techniques. They developed better metals. They developed the ability to shape them, more precision, more complexity, the ability to make machines and tools out of iron. And eventually that led to the machinery of the Industrial Revolution, where we find machines today, machines being used to build machines that in turn produce the products that we see around us. So the foundation of the material foundation of our industrial civilization is based on the machines that came out of that line of development, step by step, and has led all the way to the dominant nanotechnology in the world today, which is nanoelectronics. Not usually called that, it's just the electronics you find in your cell phone, now deep in the nanometer range. So when people ask, well, what has nanotechnology done? I say, well, if Intel had decided to brand their products as nanotechnology, we'd all be saying nanotechnology is great, it's what made the information revolution possible. But because the word wasn't applied, and people think that words mean something, which often they don't, there's this confusion about what the results have been. So the prospect is for, roughly speaking, a recapitulation of this, starting with materials, many of them biological in origin, like analogous to wood, and using those materials to build atomically precise machinery and tools on a nanoscale, using those tools to build better tools, and working towards something that looks like automated industry, a reinvention of factories. I think it's important to recognize how far we've come. Sometimes people think of atomic precision in technology, it sounds like something futuristic. No, it's chemistry. Chemists have been building atomically precise structures, and for more than a century they've known what they're doing. They represent the structures. Here are the atoms. Here's how they're connected. And that process has gone from a handful of atoms to dozens, to hundreds, to, in recent years, millions. There's now one technology, structural DNA nanotechnology, in which people can make a design subject to certain design rules, and it's like carpentry. You specify where the pieces will be, and the pieces are segments of DNA double helix, just use it as a structure. How they're held together by pieces called staple strands, where the strands are exchanged between two helices. And the result is the ability to make everything from, let's see, we have a little smiley face, which appeared on the cover of Nature when this particular breakthrough in structural DNA nanotechnology came. And you can see shaped like a flask there in a bundle of rods, and there's a box with a hinge that will open and close, and just a growing range of nanoscale structures with millions of atoms precisely arranged. So atomic precision is not new. It's instead a very old but rapidly advancing area of technology, which raises the question, where can we go with it? So the prospect is what I think can be called molecular systems engineering, or macromolecular systems engineering, working with large molecules. And the two questions, as is often the case in technology, is first, what can we do today with accessible tools? And then looking at the potential applications, where can that lead? What can we do with, what will be enabled by further progress? Can we build better tools that build better tools? And where does that go? So, looking at the present state of the molecular sciences and the components that can be used in molecular systems engineering, we find a very wide range of precise structures. There are sometimes atomically precise quantum dots, clusters of atoms with metals in them, active catalysts. The famous carbon nanotubes have precise structures over certain regions. And a lot of this work has come out of the area that is called nanotechnology, out of all these different areas, much of which can be described as material science. Oh, I should mention, I was saying that that the dominant nanotechnology is nanoelectronics, but it's not called nanotechnology. The dominant area of atomically precise nanotechnology is not called nanotechnology either. It's called chemistry or molecular biology. But those names predated the term, and so they've kept the names. So these components have a very wide range of functions. They chemical transformations, taking light and transducing it into electronic effects, vice versa. You find structures of this very general kind, nanoscale structures, being used in advanced photovoltaics that are currently in laboratory development, potential applications in electronics and various kinds of instrumentation. But a problem has been, how do you put these together? And one answer is to use structural DNA nanotechnology and related technologies to make frameworks. frameworks that can be large enough to hold many components, can have sites that bind particular components, and that can be used to move from having scattered components to a phase of engineering development. And if you look closely at these things, you find that they're very different pieces of technology. They have different limitations, different strengths. They're complementary. And at present, there is the foundation in place for a new field of engineering. We have an enormous amount of knowledge in the molecular sciences, but what the mode of activity is not one we're waiting for technological breakthroughs. The need is for a new mode of organization of research, which focuses on putting pieces together for engineering purposes. Science explores, engineering builds, and it requires a different approach and different funding structures and a host of differences that often lead to a lot of cultural clash and confusion. As anyone who's in R&D will know, you have your engineers here and your scientists there, and they seem to be talking about the same thing, and yet they can't communicate. And I've spent a lot of time thinking about that problem, and there's a chapter in the book that is a contribution to the war of science and engineering and helping mutual understanding, which I think might be useful. So today we have components. We need something like circuit boards to build systems. So with an engineering discipline growing out of these capabilities, then the question is, where can those go that can really make a large difference in the world? So a path, again, using tools to build better tools. Early chemistry is sort of analogous to the hand axe, small, fairly simple things. Today, we're, I think, clearly up to a level that looks like blacksmithing. You can compare the structural DNA nanotechnology to carpentry, as I did. It's pieces, and you systematically put them together. And where this technology can go, and where the tremendous transformation of civilization comes from, is in reinventing factories. Because physics principles seem to really physics principles work very well for fabrication with molecular building blocks at high frequency using atomically precise components. This is what computational modeling tells us, engineering principles tell us, and I think it's important to understand that. So, keys are nanoscale machines and molecular components. So, what are the basic principles? Well, nothing very mysterious. It's almost embarrassingly ordinary. Now, chemistry, as it's practiced today with molecules that are moving in an uncontrolled way, is a very difficult art. Hard-won advances. There is, however, a prospect downstream of guiding the motion of molecules with mechanisms so that the parts that go together are the parts that you want to go together. And at that point, the technology looks like factories. So in factories, you find machines that move things. The problem of moving things is pretty much the same, regardless of whether it's small machines moving small things or large machines moving large things. And so the prospect here is using mechanical motions to guide bound molecules. Reactive molecules will bond when they come together. Well, you bring the right ones together, and the result is a larger structure. So small molecules together make a larger structures together make a larger one, and so on. So I think it's because at the base of all this is atomically precise machines. It's important to get to demystify the subject, to make it concrete, to understand how much can be understood. It's important to understand what it means to have nanoscale machinery. You know, in factories you find you find machines that put parts together, and in software you find that there is the ability to display videos in PowerPoint, except that compatibility problems lead to this being a static image, because software, unlike ordinary machines, often doesn't work. So this is supposed to be a video, and it will start moving when I click, and we see nothing. But if it were working, you would see this rotating. You'd see various devices going boom, 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 boom. Picking up things, putting them there. Picking up a pair here, putting them there. Simple, repetitive motions. Turntable moving things from station to station. Pieces coming in on rotary trays, and you know, something stabs down, moves it over here, puts it there. And coming out the end are plastic spray bottles. You know, so you have hundreds of millions of these little plastic spray bottle things with the little lever and the little pump and all the tubes and so on, a little spring in there. Where do those come from? Well, they're not made by people sitting there, you know, putting pieces together. Instead, people have made smooth, automated systems that have moving parts that move parts together to make things. You have machine parts that put product parts together. So that is the story behind manufacturing. And countries that still do manufacturing, like China, there are courses. You go to a bookstore in China and you find a whole floor, huge bookstore. This is in Shanghai, a whole floor where some of the books are in English and the rest are interspersed with others that are clearly on the same subject. And it's about manufacturing engineering. Go to MIT, you find a few books there. I found a few courses. But people who understand manufacturing, I think, will perhaps take to these ideas very readily. We shall see. So, machinery. To understand what can be done, it helps to sort of focus in on basic pieces, examine those in detail, and then make some generalization. So some of the relatively complicated things that one finds in machines are things like planetary gears. That's a thing you find in a screwdriver. You have a rapidly rotating motor and it turns a small shaft, and sort of hard to describe motions that you'll see in a moment occur, and you get a slowly rotating shaft out the end. So you have a drill that's turning with high torque here and very fast motor. You also find these in automobile transmissions. Another device, differential gear. You find those in automobile transmissions. You have a shaft that's driving the wheels on your car, and one wheel has to go further as you go around a corner than the other. So how do you have a shaft that comes in that turns both wheels with force and lets one go further? Well, that's a trick. It's done with the differential gear. Leave that as a mystery for people who are interested in mechanical puzzles. And then spur gears. Okay, so planetary gear. That's an atomically precise design, atom by atom, that comes out of a computational modeling exercise. There's another structure, has the structure of a differential gear, likewise spur gears. And these aren't just pictures. These are the results of computational chemistry software being applied to structures that we can't build yet, but we can understand them. Physics tells us how these structures will behave or can behave if they're made, which is a different question from how do you make them. So this is an example of how one can have an insight into classes of machines that are understandable, very straightforward, but beyond the state of the art. And if one can make machines like that, and motors, and so on, it's like in digital logic. If you have transistors and a way to wire them together, and a power source and a clock and capacitors and a handful of other components, you make billions of them and put them together, and you have a computer. Well, in mechanical engineering, if you have a certain range of components and you put many of them together, you could have a mechanical, robot arm, or a machine that rotates and stamps and produces, puts things together like a plastic spray bottle, or something else. And again, computational modeling. Key point. The frequency at which machines can operate depends on their size. If you have a large machine, it executes motions at a certain frequency, if it's moving at a certain speed. If you have a machine that's half the size and moving at the same linear speed, same meters per second, well, if it's a wheel, in the time that this one goes around once, this one can go around twice, because it's going half the distance per rotation. Scale down by a factor of 1,000,000, the frequency increases by a factor of 1,000,000. Make a machine that's productive, puts parts together, and takes, let's say, a year for a system of machinery to process its own mass in parts. Scale it down by a factor of 1,000,000, and a similar machine could process its own mass in parts in 1/1,000,000th the time. That's 30 seconds. So productivity increased by a factor of 1,000,000 simply because of small size. So atomic precision and scale, one affects the quality of products, the other has a lot to do with throughput. And as I was sort of saying before, engineers know that if you could make a certain range of components, that implies the ability to make a certain range of systems. So building up from this base, understanding components, what they imply for feasible systems, One can go through design exercises, scoping out volumes and power flows and materials and frequencies of operation and needed data in and cooling and a whole host of other concerns that engineering training leads one to worry about. Can architect systems that are a lot like 3D printers. Box, power in, data in, materials in, motion, things moving inside, little bits of material being organized to make patterns. Patterns that can be within some certain limits, any shape that you want. But where a 3D printer makes typically shapes of plastic, a machine that is instead working up from the molecular scale can make a much wider range of materials, extreme precision, and instead of getting a plastic object, you might get a tablet computer with 1 billion processor cores, because you can make finer structures with atomic precision than can be made in semiconductor fabrication today. Or carbon-containing molecules in, arranging parts, and out comes a very lightweight, extremely strong panel of material that can snap together with others, and when you put them together, you have the wing of an aircraft that weighs 1/10 as much as they do today and yet is stronger, and that leads to, well, let's say the ability to outcompete the present aircraft industry, if you can make systems that way, and if it's inexpensive enough, which is another story and also the case. So a question that often arises in thinking about nanoscale devices producing things is, how do you make something large? You can process a lot of material by simply having a lot of devices. The devices are very productive. If you have a trillion of them and they operate at 1 million cycles per second, it's, what does that multiply out to? A very large number of parts per second. So you can have very high throughput, but how do small parts become large parts? Well, if you have many small parts and put them together pairwise, they're now twice as large, and so on, and so on, and so on. And 16 steps, or four steps puts together 16 pieces, gives you 16 times the mass. 30 steps is 1 billion components. And so the number of steps of convergence to go from molecular size to macroscopic is fairly modest. Another picture, if you think about molecules coming in as raw materials and going from an input side through very small machines and being made to larger building blocks and so on, trace a single molecular fragment through it. It goes through following some kind of convoluted path, and eventually large parts being put together. It looks like a conventional factory. If it's moving at 1 millimeter per second, which is a very slow speed, and the distance is 1 meter end to end, then the time required to get from one end to the other is going to be, not very many thousands of seconds. So 1 hour processing time would be enough to go from nanoscale components to large products. Now, how long does it take raw materials to go through the global supply chain, through mines, refineries, fabrication of wire, and over here to make motors and the motors? Yeah. That's a very large and slow process. The prospect is compact, fast, and greater capability. And of course, not just making two-dimensional things, but complex three-dimensional objects that, again, are put together to make larger structures that can serve functions in engineering systems. And this is a sort of an arbitrary object that might have considerable computational capacity, well beyond anything you see today. But one of the most important kinds of products of any manufacturing technology is the components and systems needed to make more machinery for that manufacturing technology. If you look at the world's overall industrial system, you find that collectively all of the factories can make all of the parts for all of the products that you see, and can also make all of the parts needed to make more of all the machines needed to make more factories. That's a collective property of the global manufacturing economy. With nanoscale machinery, you can have a desktop box, sort of like this 3D printer, which has more moving parts than the global economy does. So one can actually have machines which can make products that are the same kinds of products needed to make those machines. So you produce a certain number of modules, plug them together, and now you have another factory. And that self-applicability is a basis for very low cost. If you have low cost of raw materials, which turns out to be what the analysis says you have, small amounts of mostly common materials, modest amounts of energy, negligible labor, and the cost of the machinery is determined by, well, it's a little hard to describe. It's a looping process where the initial capital cost is amortized over a very large number of products because machines can be used to make the same kind of machinery. And the initial cost is diluted to the point where the costs are very close to the cost of the raw materials and energy. You end up with costs like, well, let's say maybe $1 per kilogram for products that outperform anything in the world today. $1 per kilogram for example, a computer with a billion processor cores. $1 per kilogram for sheets of photovoltaics that were many, many square meters per kilogram. And the materials are, they come out of your machine in rolls, and it looks like black plastic. And if you unroll it on a surface and you know, trigger it to go into a relaxed state, the sheet softens and adheres to the surface, and another trigger and it solidifies. And so it's a lot like a coat of paint. You can put it down on a road surface, except that it takes 30% of the incident solar energy and converts it into electric power. Well, that's the kind of product that can be made if you have atomically precise control of fabrication of structures. And the cost can be low. And that kind of product by itself is enough to point to a potential revolution in renewable energy. So the characteristics of this kind of technology, downstream, after layers of incremental development, is precision. Precision leads to a clean process, not a whole lot of waste, because what goes in, you know, comes out as products or as very controlled, precise byproducts. If there's less hydrogen in the product than in the input, then an output might be, for example, water. I explained why rapid processing, you know, follows from scaling laws. Low resource consumption largely follows from the ability to make very strong, lightweight materials from things like carbon and silicon dioxide. And if you look at things around you, most things are structural. You know, this is a structure, happens to be a transparent material. More structures. This is a mechanical wind-up watch. And its moving parts, the inside of all of them, is a structural material. If you take structural materials and replace them with something else, you've replaced most of the mass of the things that people use. And if what you replace them with is inexpensive and lightweight and strong, then you can lower the cost and improve the performance of a very wide range of products. So that's where resource efficiency comes from. And of course, being able to build with atomic precision opens new realms of technology. For example, in medical instrumentation, the body is made of complex molecular structures, and indeed molecular machine systems that build and repair other ones. Medical interventions with pharmaceuticals are about atomically precise structures that go in and interact with this molecular machinery. The ability to make somewhat larger devices that are more complex, can interact in a more controlled way, you know, sensing, flipping some switches and acting. Consider a cancer cell that has a surface that looks a lot like a normal cell, but some differences. Measure a number of features and do some statistics on them, and it'd be possible to distinguish very reliably a cancer cell from a normal cell, and then to kill the cancer cell and do nothing to the normal cells. So that would be a mechanism for destroying those cells while having no side effects. And for infectious organisms, the differences are even larger, and people worry about the emergence of new diseases. Well, it might be good to have the ability to rapidly produce the technology of essentially sort of artificial products that are like what your immune system does. In any event, in particular, for the manufacturing technology itself, which is distinct from the products, the manufacturing technology itself is a matter of textbook physics and chemistry, and the productivity comes from elementary scaling laws. So, huge production capacity. I said something about, I think, advanced electronics, light materials, aerospace, medicine, said something about solar electric power. And with a technology that's past this threshold, there's the potential for rapid deployment of the manufacturing capacity for reasons that I outlined before, the self-applicability of the technology. Therefore, rapid deployment of products, which can include the manufacture of the things that are needed to make a rapid transition to a zero carbon emission economy. And something more than that. If one wants to point to one critical global problem where the real challenge is our ability to make things, our ability to process matter and energy more effectively, it's the greenhouse gas problem, where we have on the order of 1 trillion tons of CO2 dilute in the atmosphere, and increasing year by year. Here's the famous Keeling curve, the level of CO2 oscillating every year with the ecological cycles, but increasing steadily as people inject more CO2 into the atmosphere. All the reasonable expectations say that the future looks like that. And if one studies geophysical processes, if one were to, well, if you cut back on CO2 emission, the levels continue to increase, but more slowly. If you stop CO2 emission, the levels decline. The stopping is way beyond what is reasonable to expect in the next few decades. The levels decline through geophysical processes at a rate that takes generations. And during all of that time, there's more heat going into the oceans. The ice continues to melt at a rate higher than we see today because the CO2 levels in that era would be higher. So that is not a very attractive future. The only way out of that future is to remove the carbon dioxide from the atmosphere. But it's 1 trillion tons, it's diffuse and dilute, and so doing that is difficult. Quantitatively, the requirement is something like 10 to the 21st joules of energy. That's the thermodynamic work of compression to take the CO2, put it to liquid density, whereupon it can be packaged and gotten out of the way. That is the equivalent of 3 terawatts of electric power for 10 years. 3 terawatts of electric power is the total power generating capacity of the human race today, worldwide. It's not a practical engineering prospect to be able to double electric power generation capacity, switching entirely to renewable zero carbon energy, replacing what we have and doubling at the same time, and building all of the devices necessary to actually capture CO2 and compress it efficiently. It's beyond, for industrial technology to repair its own damage seems to be beyond its capacity. But, what's needed? Well, how much solar energy would you have to collect? Well, there in the middle you see a square that represents the aggregate photovoltaic array area necessary to collect 10 to the 21st joules, 3 terawatts for 10 years, and provide the energy necessary to do this job. If we had a revolution in our ability to make things, we'd be able to undertake economically the task of reversing the greenhouse gas problem and putting the Earth back to some state more like what it was, with the kind of climate that is compatible with existing ecosystems and agriculture and human life as we have known it. So the prospects, basically, this is saying global warming is in essence a manufacturing problem to the extent that a revolution in manufacturing can solve it. So the prospect is developing macromolecular engineering. There's been rapid progress. The need is for a more focused, integrative engineering effort on top of the existing science. That leads to directed self-assembly. I could say more about that in the book. There's an Appendix 2 says quite a bit about pathways forward and incremental progress and what some of the intermediate stages look like. But incremental progress from there to directed fine-grained fabrication to scalable, atomically precise manufacturing technologies, small systems that can be used to build more hardware of the same general sort, scaling up to larger systems, and many of them. And that's what leads to revolutionary applications. We're not there, but we can see and outline a path forward and can see in considerable detail ways of doing the advanced atomically precise manufacturing. Will it be done that way? Well, of course not. I said earlier, you can't predict the future of technology. This is not a prediction about the future of the technology. It's saying here is what the laws of physics permit as can be understood through the application of engineering principles. It says that people with the right tools could build these things. What will happen? Something better. You'll have smart people who have insights and discoveries and inventions that no one has yet, and they'll build systems that are far superior to these very mundane, analyzable, conservative engineering projections that we have today. So this is not an effort at predicting what will happen, it's an effort at understanding the lower bounds on what physics and engineering permit with to the extent that this is a correct analysis, a firm expectation that what can be done in the future will be more and not less. So the next steps that I very much would like to see, the first and most important one is more understanding. There's a methodology here that's based on established knowledge. It's a matter of asking the right questions, evaluating the answers, asking whether there are other questions that must be asked, which is a bit more difficult, and assessing whether or not there is a real prospect here. Now, there has been a lot of confusion about what these concepts are. You may have heard of ideas that nanotechnology and atomically precise manufacturing is about swarms of little bugs. Well, this isn't about swarms of little bugs, it's about factories. We hear that nanotechnology is sort of equivalent to material science. Well, that's an aspect of nanotechnology, but it's not this. It can contribute. The United States National Academy of Sciences in 2006 issued a report which actually consisted largely of a review by a committee of the National Research Council. They were asked to do this by a member of Congress. It was largely a review of the work that was mentioned earlier. It was my MIT dissertation and another year's work in this thick book of applied physics, and the committee reviewed it, and they said we should have a focused research program in this area. Congress thought that it had already funded that, but the bureaucracy in Washington decided to do something else, and when they got this recommendation saying they should do what they'd been funded to do, they put it away. You still haven't done that, and there's ongoing confusion. And the book discusses that. So what's needed is an assessment of the actual concepts, the actual state of the art of understanding, which I think will come to the same conclusions that the U.S. National Academy of Sciences Committee did, which is there's a real prospect, we should have a focused effort. Given that, making plans, there are road mapping processes like what the semiconductor industry uses to coordinate development so they fit together, so that developments of different kinds can be combined to build functional systems in a next generation technology. And that in turn can be a basis for focused development. I think the case for this will be compelling when the right questions are asked and considered, and there is a conversation about the implications and the significance of it. So the book I just mentioned is Nanosystems. It's, if you want, looking for a book of applied physics that discusses the thermodynamics and statistical mechanics and molecular dynamics and systems engineering and a whole lot of stuff. It was a bunch of work, and a lot of people think it's pretty good, so I'll recommend it. A few years back, I was the co-technical leader of a road mapping project, which was hosted by several of the U.S. national laboratories. This came out with a document that's available in PDF online for free, which is a first effort to look at the present technology base, paths forward toward productive nanosystems, also known as atomically precise, at least in the advanced forms, atomically precise manufacturing. So that's a useful resource. And of course, best of all, now available in the Dutch language, is the book that makes a very strong effort to make these ideas very clear, very accessible, show scientific grounding, sort out mythology and fantasy from what we understand, how we understand it, what some of the implications are, and its purpose is to provide a framing for a conversation that I think the world very much needs to have, to understand whether the 21st century can be something very different from what we've been planning. Thank you.
Eric, thank you very much for a fantastic lecture and sharing with us how manufacturing can develop from a macroscopic manufacturing to atomically precise manufacturing. So the lecture is open for discussion.
Yes.
And who would like to start?
Great, Drexler. Thank you.
Thank you.
What I understand is you want to see manufacturing on nanoscale, atomically precise, and you have certain goals that have to be fulfilled. So those nanofactories have to have modular design. They need to perform assembly, chemical reactions, whatever, in a programmable way. They should be able to replicate, so to make copies of one another. They have to have modular design. And as far as I know, we have something like that around us already, and it's called biology. So basically, if I understand you correctly, you're asking for a system that is some kind of an alternative version of biology, another biology that, in contrast to the one we have, will be able to synthesize molecules, arbitrary molecules, because what we have now is basically directed towards just replicating itself through Darwinian evolution, and something of that kind.
Biology has been an inspiration in this area. It provides examples of atomically precise molecular machine systems that, under digital direction, manufacture components of more machine systems. Genetic information directs ribosomes to make chains of amino acids that fold up to make little solid polymeric objects that we call proteins. So it's a proof of principle at that level, can provide some useful materials and techniques in the early stages where self-assembly is important. And beyond that, almost everything is different. To speak of the inspiration aspect, birds were an inspiration for people to think about human flight. And we learned a lot from birds. We learned that having some sort of a body with wings coming out with a certain aerodynamic shape was good. That it was possible to have a structure that would glide at a shallow angle, not dissipating much energy. What was involved in that kind of shape. But we still don't understand birds in complete detail. We understand jet engines much better than we understand muscles. We can build jet engines, and we can't build muscles. And so what we have today are aircraft that are almost entirely unlike birds, despite having been inspired by them. And it's a similar situation here. Different materials, and, I don't know, different in almost every detail. So I think the biological analogy is an interesting starting point, but it has to be set aside very early if one wants to actually understand the concepts.
Yeah.
Hey, thank you, first of all. That was very interesting. I should probably preface this with saying that I have no idea what I'm talking about. But if I imagine taking some kind of raw material and then rearranging its molecules in whatever way I feel suitable, then I assume that takes some amount of energy to tell those molecules where to go, what to do. And that is probably not negligible. So I'm wondering.
Not,
so you
not
probably
negligible. Excuse me.
Yeah.
Yes.
So I was wondering, how much energy does it actually? So what's the relationship between the energy that I put in and what I get out, and also how much does the end product depend on the raw material that I have? So can I just take some dirt and make some sandwiches?
I'm sorry. You claim that you don't know what you're talking about. I'm afraid that you do, in fact, know what you're talking about. So that's a very good and appropriate non-target question. These systems are all subject to the laws of chemistry and thermodynamics. To transform materials into new forms takes energy. To process molecular materials, simple materials like carbon dioxide, water, silicon dioxide, hydrocarbon like hexane, various simple molecular inputs. Actually, silicon dioxide, you better dissolve it first. But to process those involves rearranging chemical bonds through chemical means, and the energies required are chemical level energies. The kind of energy required to smelt aluminum, the kind of energy released by burning a fuel. That magnitude. You pay a bit more because you need multiple stages that are thermodynamically irreversible. They have to be downhill decisively to have deterministic behavior. There's an energy cost for that. As you say, it's not negligible. It's also not huge. The energy cost is somewhat more than for making ordinary materials, but the materials are so much more efficient that you need less energy per unit of product because there's less material needed. And just a comment on the entropy side. Clearly, one would, in many cases, start with something that's a liquid, disorganized. Atomically precise molecules, and small molecules of any particular kind are, by definition, atomically precise, but disorganized. What comes out the other end? Precise organization, reduction in entropy. Well, here's an example of taking a disordered liquid and producing a very low entropy structure. Take water, put it in a tray, put it in your freezer. Water molecules are arranged into ice crystals. Most of the organizational entropy is removed by that patterning, and the energy required is significant, but it's not large. And so the entropy aspect is part of the thermodynamics, but it's not huge.
Thank you for your interesting talk. Actually, I have two small questions. So first, suppose we have a machine made by nanotechnology, like the gears you showed in the slide. I wonder how much would be the mechanical efficiency? Would it be similar to what we are using now, or will it be much smaller or bigger or something? And the second question is every chemical element in this world suitable to be manipulated in a nano scale? Yeah, as far as we know, carbon and silicons are the successful examples using in nanotechnology. But I wonder whether oxygen or other gas element can also be used in nanoscales. Thank you.
Well, a wide range of oxides, and also, so the elements that seem to be most useful are carbon, hydrogen, oxygen, nitrogen, little fluorine sometimes for shaping a surface where you want something bulkier than a hydrogen, likewise sometimes perhaps chlorine. Silicon is useful, sulfur is somewhat useful, phosphorus is somewhat useful. And beyond that, the main elements of, well, boron is kind of has some special utility. Many of these are not necessary, but they're available and convenient. The more exotic elements are mostly useful in very small amounts as catalysts in chemical transformations. The fact that carbon happens to be able to make conductors that are better than aluminum is also good, particularly as an oxide. The fact that carbon in nanotube form happens to be more conductive than copper, just by luck, means that the other main material that we use that isn't structural is, things for electric conductors. Turns out that carbon can do that too. But okay, my mind is gone. Your first question, I recall, was excellent. If you could say 2 words to remind me of what it was.
Okay, the first question is about mechanical efficiency.
Yes, thank you. That's the necessary 2 words, mechanical efficiency. Yeah, the class of devices that I showed there, actually remarkably efficient. In particular, the planetary gear. Efficient planetary gears in the world today with metal parts and lubricants can have energy conversion efficiencies. Shaft power in, shaft power out, and the question is how much comes out as heat instead of as power because of friction. Can be in the high, 90% up toward, forget the exact number, it's up toward 99% for good ones. That's surprisingly high, perhaps. In the case of the atomically precise structures, first of all, they can move very slowly and still have a very high power density. This factor of 1,000,000 that I mentioned in terms of speed up also translates into a factor of 1,000,000 increase in power density given a certain rate of motion. And it turns out that the energy losses are the rate of power loss is proportional to the square of the speed. So if you slow a device down by a factor of 100, the power losses to vibrational energy, phonon scattering, a whole bunch of different little loss mechanisms, drops by a factor not of 100, but a factor of 10,000. So and given that the baseline, you have a million-fold advantage in power per unit mass, and if you throw away a factor of 100, you decrease the friction by a factor of 10,000. So think about those numbers. It's a very nice place to be for engineering. And the result from just actual molecular dynamics computations indicates the efficiencies at slow motion, extremely high power density, those go together, can be higher than what we see in conventional devices. You don't have liquids being sheared, and therefore that fundamental loss mechanism isn't there. The mechanisms for lubrication, in effect, it's different physical principles that don't have the same dissipative quality to them. There's dissipation, but it can be much smaller.
Short question, but maybe a long answer is required. But the dangers to human health, can you say something about that, please? Inhaling nanos may be bad for your health and lung system.
Well, as I said, the term nanotechnology, since I introduced it way back when, has been stretched to cover pretty much everything that is nanoscale and involves technology that people have decided they want to promote as nanotechnology. So the term has been applied to very small particles. For example, people are making socks that retard bacterial growth because they have nanoparticles of silver on them. Okay? Well, how do those nanoparticles retard bacterial growth? Well, they have a lot of surface area, and silver ions dissolve, and silver ions are toxic to bacteria and to other organisms. So the purpose of those nanoparticles is specifically to be toxic. There are many other nanoparticles which are to serve some other of many functions. They have many applications. But they can get into the body. They can reach places that they can actually cross the blood-brain barrier and end up in the brain. Some of them, others not. Depends on the specifics. And so they raise a whole lot of what are essentially toxicological problems. And they're difficult problems because chemical entities, a particular kind of molecule, you know what you have, you can test it, you maybe don't learn all that you wanted to learn. Perhaps you should be cautious about ingesting new chemicals. But at least it's fairly straightforward to do the studies. Nanoparticles, is it larger, smaller, slightly different composition, different surface, many different variations, much harder to do the science of toxicology. But in this context, the key point is there aren't any nanoparticles. The nanotechnology of chips, it's a nanotechnology, but it's produced silicon chips with one chunk of electronic material, no free particles. In this case, the manufacturing systems are integrated systems with no free pieces, and the products. Most of the products would be, at least as envisioned here, would be more or less conventional sorts of objects. Again, large, solid things and not nanoparticles. All sorts of horrible things could be made, but they don't have to be made. They're not inherent to the technology.
Thank you. I can assume that nanostructure is very sensitive to external electric and magnetic fields. So if you make a very big, for example, such a nano device, and you make it very important in everyday life, then my everyday life is very dependent on those external magnetic and electric fields. So is it very risky to make everything nano devices while they're so
actually, it's possible to make nanosystems that are exquisitely sensitive. Scientific instruments can be made that detect very small fields And we know that electronics can sense very weak electric and magnetic fields, which is how Wi-Fi works. But there's no general principle that says that objects that have fine detail in their structure, there's no general principle that says that they're particularly sensitive to electric or magnetic fields. If they're not magnetic materials, in fact, they'd be very insensitive to magnetic fields. And if you don't have a lot of iron in them, there's not a whole lot of use for a lot of iron, tend to be non-magnetic. As for electrical fields, if you have a layer of say the equivalent of aluminum foil around your box, electric fields don't even penetrate. So a combination of insensitivity and, where needed, shielding can provide what I think you'd like to see, which is robust systems that are reliable.
Can you please pass the microphone to the back, Paul?
Yeah. Well, it's a great honor to be talking to the godfather of nanotechnology himself. So it's pretty awesome. I had like two broad questions. The first question is, you said that it's like pretty futile to try and predict future technologies or how it will look precisely. But like you also said, atomically precise manufacturing is possible. And I just wanted to ask, since you have a pretty unique perspective in that, what are the signs, or what would you like look for to know that atomically precise manufacturing is nearby, or let's say relatively close?
Well, okay, so first, what one shouldn't look for is atomically precise manufacturing itself. There's a path through a lot intermediate technologies that at first really don't resemble these advanced systems. The later ones that have the same quality or approaching that quality would be very small. Okay, microscopic systems that make little microscopic products in small quantities would be a very reasonable development. It's also possible to have large-scale production that looks more like the chemical industry, but that's a separate question. And also doesn't look like desktop 3D printers that make amazing products. So the natural expectation is that there will be progress that doesn't look like the end point up to a threshold of a scalable technology, at which point one should expect there will have been a lot of design work done in anticipation of the tools. In the semiconductor industry, they don't develop tools for making a new generation of chips and then say, oh my, what will we build? They have the designs and the fabrication techniques ready at the same time. That's part of what road mapping does. Ready at the same time and ready to go. So I think we'll see the fabrication technology advance, design being done in parallel, and then implementation, and of course debugging, because things usually don't work the first time. But if you if you have a good design, you can usually fix it after testing it. So I think that what one should look for is well-grounded people in science and technology reporting progress, and not making up hype, but saying, here, we've made this device, that device. Increasingly, engineers who know about systems explaining how, what the next generation of technologies will look like in concrete detail. Not, hand-waving, gee, we've made this thing in the lab, and it'll give us a great battery. Well, usually it won't. But that kind of work. Think of the space program. You didn't get a single gram of moon rock back until it was at an advanced stage. For years and years and years, if you'd said, we're going to measure progress in space flight to the moon by how much moon rock we get back, you'd have no sign at all of success until all of a sudden, Neil Armstrong and Buzz Aldrin came back with a box of 100 kilograms of rock or whatever it was. So, you have to have the right metrics, and in many cases, looking at progress reports and investment that is properly focused is a very good indicator. I don't think that for alert people, I think we're unlikely to have a surprise, unless there are, secret militarized programs, which I think it may be possible to persuade people are unwise, and I think would be hard to keep secret, which is one of the reasons they would be unwise. So my expectation is one will be able to follow the developments in the press and the scientific journals, and that would be the best approach.
Oh, nice answer. And a second question, it's a little broader and maybe not, it's a bit unfair, but I just wanted to like ask your perspective on this. The title of your book is called Radical Abundance, and if this technology ever, you know, if it happens, I mean, probably the world will be living in a quality of life much higher than we can imagine right now. But what will the effect of this technology be on the wealth gap? Because at the beginning, I mean, these technologies, yeah, on the wealth gap. I mean, we might all be a lot richer, but I mean, what will the difference be between the super rich and
all a lot richer on the average? And as I say, Bill Gates walks into the room, and all of a sudden, the average wealth per capita skyrockets. It doesn't necessarily help anyone. You know, something that in putting together this talk, I wish that I had included some of my slides from a talk that I gave yesterday, is on some of the disruptive implications. Again, the purpose in this book is to frame and show the basis for a potential technology. It then unfolds to ask, what are natural applications of it? What will it enable? What will either happen or be stopped? Not just, doesn't happen, but rather either people will do it or people will want to do it and someone else will stop it. Okay? That's not making a prediction. It's saying there's a force that either will go somewhere, or if not, there will be a reason. So that's sort of the style of analysis in framing questions about, among other things, the wealth gap. We've seen in the world that rising automation, rising productivity, per capita, that in principle could make everyone have, more material wealth. That what that can do instead is to leave whole categories of people unemployed and impoverished. Well, if computational technology and manufacturing technology goes far enough, you'll have machines that are better at, a very wide spectrum of things that are done in the economy. The potential for an enormous wealth per capita. And if we retain the same sort of economic frame that we have today that treats people as machines for making things, you will find that many of those machines are in very bad condition. If, on the other hand, we recognize that human life is not about using people as machines to make things, then perhaps we can make machines to make things and have them make things for people and be rather better off, which is a way of saying that there are enormous questions of economic structure and governance. Well, one of the prospects here, if the technologies are applied in a natural way, not stopped or moderated, is for a relatively rapid collapse of a wide range of industrial, international, intercontinental supply chains and all of the jobs associated with them. A collapse of demand for lead, tin, cobalt, nickel, manganese, tungsten, and a whole lot of elements that are part of the export earnings of third world countries that are mineral rich can collapse. On the other hand, with access to highly productive technologies, you don't need the export earnings because you're not buying manufacturing goods. You're downloading open source designs for your equivalent of a 3D printer, but a far more capable machine, and you don't need those imports. So there's the potential for great economic devastation coming out of the very technologies that could raise the poor of the world to a higher standard of living than the wealthy have today. And there are choices we can take that lead to that latter outcome. Likewise, there are paths that lead to an unpredictable and risky arms race where people are basically preparing to fight wars over resources that are no longer important, or a world in which there has been some thought given beforehand and a recognition that national interests are different in a world where the main threats are the disruptions of abundance rather than fighting over dwindling resources of Earth. They're two very different futures. And planning military and national strategy for a world with APM has to be rethought, not treated as a small modification of a scenario of United States and China struggling over Middle East oil or something crazy like that. And part of the purpose of the book is to frame some of these questions, to point out what are the coherent scenarios, some of the pitfalls in thinking which, if we just walk blindly down some path, could lead to bad outcomes. So I hope we'll have a conversation that addresses some of these questions, including the wealth gaps. That's a long answer, which is partly to make up for topics that I omitted in the talk that are very much present in the book.
Thanks a lot.
Thank you.
Well, you managed to talk something about the main subject of my question, but if humans could use, or they could really use some facilities to produce some products on a nanoscale, but what will happen if animal or plant life or bacteria, small plant animal life, would adapt or use those same facilities we are creating? And what kind of issues would be arise? Aren't we creating bigger problems than the ones you try to solve with?
The prospect is for solving some enormous problems and creating enormous problems, and I'm not sure which of these are larger. It's a major shift in the situation that we will apparently be in. But you raised the issue of the rest of the biosphere, the plants and animals, and the relationship between, I will describe it as the rest of the biosphere and this kind of technology, and by comparison with industrial technology. So, where are we today? Today, there is, destruction of land through mining, emissions of CO2 that are changing the climate at an increasing rate. People cutting down forests because they want wood, they want more agricultural land. There's very little fertile land left. You can't expand agriculture now by putting new land under the plow, except very marginally. The human race is already consuming something like, estimates vary, but something like 25% of the total photosynthetic primary production of the biosphere. We're not sort of nibbling at the edge of the biosphere, we're swallowing a lot, literally swallowing a lot of it. And biofuels, I tend to make that worse. So that's a situation of an enormous impact of our present industrial agricultural system on the natural world, and it looks like it's sort of grinding it down. It's hard to see how that collision doesn't lead to a very ugly result for both people and the world. In the long run, Malthus was right, but just looking at a century time scale, mere century, which may be time for gaining some wisdom, the after a century, the prospect is of being able to have a much higher standard of living for people, with actually reversing the impacts on the atmosphere of industrialization. Instead of increasing it, rolling it back. Instead of increasing the consumption of scarce natural resources, instead decreasing that dramatically. And interestingly, and what I had in mind is most important with respect to the biosphere, is the impact of agriculture. The greatest impact today is that wherever you've had an ecological system that is productive, areas of the ocean that are fertile, and you have plankton and abundant fish, large fish, what do you have? Trawlers going through, and the fish are getting smaller, and some species are becoming rare. Fish is very good for you, right? People eat a lot of fish. I eat fish. It's the parts of the biosphere that had ecological richness, the ability to support a large, intense population of plants, diverse species, animal species. Those are the areas that are most productive when you plow them under and plant maize or wheat. So much of the most productive biosphere is no longer in that form, except as little parks and reserves. But here's just an interesting little fact. Once again, this can be phrased as a manufacturing problem. Here in the Netherlands, I think it's well understood that if you build structures that have glass, and you raise plants protected from the natural environment by glass, and you control the humidity, the temperature, and the light, you're able to do agricultural production that is far beyond what you can do otherwise. It turns out that greenhouse agriculture, enclosed agriculture, can increase the yields of, for example, wheat by something like a factor of 10. No one raises wheat in greenhouses because they're too expensive to build and operate. The physical plant, the energy, and so on. Well, if you drop the cost of production of infrastructure, of hardware, of capital goods by a large factor, drop the cost of energy by a large factor, make it easy to automate the production of prefabricated structures that can just be sort of rolled out, then you have the potential to take the existing agricultural production, increase it, and yet decrease the land requirement to free up more than half, maybe 80% of the ecological footprint that we have today. So there's a prospect for having better quality food, fresh food, greater food security, all sorts of very beneficial things, organic food, you don't need so many pesticides, and do that with a fraction of the farmland, and thereby decrease the impact of the human race on the biosphere to an enormous extent. And I don't know, I care about such things, and I think that's important.
So another question.
First of all, thanks for the talk. And continuing this theme about, you know, our impact in food production, do you think with APM it would be eventually possible to find less impactful ways to produce raw material and use APM to actually build the food? Or?
Well, what the main impact is less need for raw materials overall and less need for scarce raw materials. A very large part of the physical products that we use, structures, electrical conductors, many functional materials, a lot of that can be made of carbon. And it happens to be the case that there's a lot of carbon around that nobody wants in the form of CO2. And one thing that can be done to draw down atmospheric CO2 is to convert it into useful products. There's much too much. There's far more than would be needed for that. So it's not actually a very good carbon sink, but it does say that there's no shortage. As for other materials, it turns out that one of the basic differences that flows from atomically precise manufacturing is the ability to use materials that are very strong but sensitive to flaws. Part of the reason that metals are useful is that you can pound on them and nick them and so on, and they just bend and give a little bit. But metals are much weaker than carbon materials. They're weaker than a wide range of ceramics if the ceramics are flaw-free or have a fibrous texture. Fiberglass is very strong, where glass is brittle. Well, the glass itself is strong, it's just the flaws. So being able to organize the same kinds of material, very abundant material like silicon dioxide from sand, aluminum oxide is also a very good material, sapphire. Organizing that in the right way can make what by present standards are super materials and very common sources, very little environmental impact in producing them. So that footprint can be greatly reduced, partly because of the happenstance that better control enables us to use common materials that are actually superior if you fabricate them properly.
Thank you.
A couple of people now have brought up several topics or several ideas on how this might be harmful. And I think it's pretty obvious that it could be. But since we are all nice people, we will probably all use it to make awesome, helpful things. But I mean, it really only takes one person to make some kind of self-replicating virus and kill us all, I guess. So my question would be, do you have any considerations regarding some kind of legal framework? So who should be using this stuff? Because, I mean, today I can go online and download a blueprint for a 3D gun that I can print, right? That is not traceable, and there we go.
Yes, I have a slide of that. Yes.
Yeah, so you brought up the analogy between 3D printing today, where you have the distinction between the hardware you need to actually produce the materials and the open source software blueprints of, well, the blueprint of what you want to make. So who should control the blueprints? Or who should be in control of all of this?
I would phrase the question slightly differently, but that is in many ways the key question. This class of technologies raises profound questions of governance. I wouldn't say exactly who, but I would say what mechanisms of governance are needed to constrain the applications to the most straightforward and obvious concern is people making distinct things that are very dangerous. There are all sorts of more subtle issues of economic disruption and so on, which may be more transitional than anything else. But even as you point out, even 3D printing can make weapons, despite the fact that it's at present very primitive. There are strong analogies between this and 3D printing, except vastly higher throughput, higher quality products, huge qualitative expansion.
Well, that makes it only more scary, though, right?
Yes. If you're not scared of this degree of change and this degree of additional technological capability arriving in the world, then you're not paying attention. One of the really terrible things about the last 20 years has been that people got scared of the idea of little bugs that would accidentally do something where nobody, is making anything like that, and that's been a distraction from worrying about people deliberately making things that are dangerous or are intended to control other people or kill them. Don't worry about someone accidentally making something extremely intricate that nobody has an interest in making. Worry instead about people making weapons. And if you have an arms control regime that can deal with that, then you can also, you have to be able to deal with hobbyists making, whatever. If you're able to keep governments from making destructive systems, then you must have put in place a system that can deal with these lesser threats. So I would take that particular aspect of governance, deliberate construction of destructive products, I would fold that into a broader question of arms control, which looks different from previous arms control issues, but the core of it is arms control. And that leads into a whole lot of questions where it invites comparisons with nuclear materials and nuclear technologies, and that's a very useful comparison to make in part because of the points of divergence and difference, which in turn point to the desirability. Well, once upon a time, back when, this is early 1990s, once upon a time, long, long ago, before nanotechnology became all confused, I was giving a presentation at the Pentagon, the United States, to an audience with some rather senior people in front. And in the talk, I was explaining, this raised serious arms control questions, that it's because of the nature of the technology, no exotic materials, no large quantities of anything, many different forces push, many different ways of moving forward, many different reasons. It's a diffuse technology that you can't use satellite surveillance. You can't look for missile silos or nuclear reactors or something. It's not that kind of technology. And so what I said was that this is a technology that really calls for mutual on-site inspection, as they say in the arms control business. And I said that the most effective form of mutual on-site inspection and verification is to have your scientists working together on the same projects in the same laboratories. And the people in front were nodding. I found that encouraging. I hope the culture hasn't changed too much since then. I worry about that. But that proposition that that arms control issues lead to a desire for a certain kind of cooperativity and transparency is a very strong argument. And the argument that the reasons for trying to gain a military advantage largely disappear if you have, quote-unquote, radical abundance. There are several pieces of the puzzle that go together that say that national interests really need to be given be reviewed, rethought, and I think will lead to a sensible evaluation of that. Purely self-interested, I think, leads to a more cooperative stance than we've seen in the past. Fortunately, the science is already strongly cooperative. That provides a pattern which perhaps can be expanded and made even more robust in its cooperative structure. So there's an open door there, and perhaps we will have the wisdom to walk through it and continue along that path.
Let's hope that happens. Thanks.
Okay, there is one last question because due to the time constraints.
Thank you. What I'm wondering, what about the practical problems with those nanostructures? I mean, you have like the flaws in the materials, like you said, but what about the influence of chaos theorem and that kind of stuff?
Of what?
The chaos theorem. The chaos.
Chaos theory, yes. Yeah. There are many, chaos theory is studying systems that are right on the edge of or beyond stability in a certain sense. where there's a dynamical property where it's extremely sensitive to the initial conditions. I think, many people have heard about chaos theory. You can't predict what the results are. They're within certain bounds, but the detailed trajectory is unpredictable. Engineering is largely about avoiding that. If it's a system that's unpredictable, you don't build that. In science, one takes nature as it is, and that poses questions. Some have answers, some don't. The modeling can be difficult, it can be easy. In engineering, you have the luxury of choosing the problem, choosing the system that you're working with. If the natural environment is a complex place with biology and weather and so on that can interact with materials, and you have problems of corrosion and dust and animals and so on, what you do is you put your machine in a box. You keep all that out, and you have a nice clean environment. And if you have problems of vibration, well, you make sure that the machine, you can't predict the exact vibrations, but you make sure that the amplitude, whatever the amplitude is within tolerance and can be tolerated. In digital electronics, there's always a little uncertainty in the voltages, but at every stage, a relatively high voltage is a 1, and a relatively low voltage is a 0, and it keeps on distinguishing the two, and so the noise doesn't build up. So that practice in engineering of taking uncertainty, noise, and so on, and accommodating it, boxing it, controlling it, damping it down, avoiding problems, that's really the heart of successful engineering, and that's the approach that has to be applied here to have successful results.
Okay, thank you.
Thank you.
As I said, I would like to close the discussion at this point. And we would like again to thank you on the behalf of Studium General for coming here and sharing with us. And also on the behalf of the whole audience. And as well, everybody who has urgent questions, burning questions, they can always find the answers, I guess, in your books. But also we would like, in the meantime, on behalf of the Studium General, to give you the book written by the professor from the University of Groningen.
Thank you.
Token of appreciation. So thank you very much again for coming here. And please join me again to thank Eric Drexler for a fantastic lecture.
Thank you.